So a student asked a question in class about strain hardening, and I've cooked up a fictitious situation here. I got a 1 meter rod, a 1 meter segment here between two fat ends, and I've got it rigidly attached on this end, and I've got it attached to a block of metal here, then a force sensor to find out how hard I'm pulling on it, another block of metal here with a bolt in it, and this is a rigid rod. This bolt just spins at this location, but when I turn it, it'll bring this block over, and therefore I'm moving the end of this rod wherever I want it. And I got it, the end of the rod lined up with a ruler, and I measure what the length is and what the force is. When I say the length, I mean how far over I have moved this end of the rod, how far I have stretched the rod, and I've made a graph here of the force reading from the force sensor versus how far over I moved it, and the units aren't on the graph, so I better put them in. They're in, it's in millimeters, so I guess I got room over here. So it's the stretch in millimeters. And I broke my sample. I took it as I just kept relentlessly increasing the length of the rod. The first thing that happened is the force grew proportionally to the amount of stretch. Then once I had it stretched 1 millimeter, it started the force versus stretch changed shape. And I continued, I just kept making it longer and longer, just by screwing that bolt over. Eventually, I get to a point where as I made it longer, the force sensor reading went down. And then I got to this point and it broke. At 6 millimeters of stretch, this 1 meter rod broke. So this is your fracture stress. This is your ultimate stress. They're all so close together. You can look at that as the elastic limit, and I'm not seeing, when I stretched it just a hair over a millimeter, it came out, but it was so close that that's essentially the proportional limit. And let me repeat that. Well, I'm going to do a separate experiment and talk a little bit more about these, and then also very close to the yield stress, although we could do a yield for this material. It doesn't have a well-defined yield point, so we'd probably do a yield at a certain percentage offset. Alright, so I had to throw that sample away. I loaded it up again with a new sample of the same exact material, and I played around with it, and when I stretched it 1/10 of a millimeter, and then let it go loose again, unscrewed the bolt so there was no more, I wasn't stretching at all, no force on it, it snapped right back to the original position. Same thing happened when I stretched it 0.2 millimeters, 0.9 millimeters. I stretched it 0.9 millimeters, the new sample, and then let it go, and it snapped all the way back into its original position. 1 millimeter, the same thing happened. I tried 1.1 millimeter, and it didn't snap back all the way. In fact, with one sample, once I got the 1 millimeter, I was tired of fooling around with it, and I knew it was at 1 millimeter it would snap back. I stretched it all the way up to 2.3 millimeters. 2.3 millimeters long. And then when I let go of it, it didn't snap back all the way. In fact, it remained, when I snapped it all the way back, it was still 1 millimeter longer than I started with. So I put some permanent set in it. It was permanently 1 millimeter longer than it was. And then when I playing around with that same sample again, I had to start here. It's like I got a new graph where this is now the 0 for the amount of stretch. There's the delta. This is 0 millimeters, 1 millimeter, 2 millimeters, etc. Because it only snapped back to this position. It was permanently 1 millimeter longer than I started with. So it's like I got a brand new graph. And this time, the graph went all the way up here I didn't quite hit the intersection quite right, but it went up to this point where I stretched it before, pretty close to a straight line. It went almost all the way up there as a straight line, and then there was a slight curvature. And I played around with it, and it went back and forth here as long as I stretched it, in this case less than 1.2 millimeters, which was 2.2 millimeters over from where I had put the original rod. It just didn't snap back as far. But now, if I stretched it all the way up to 1.2 millimeters, it would snap back. So I made the elastic region a little bit longer along the delta axis, and on top of that, it went up to a higher force. I could put more force on it, and it would still snap back. And this is what we're talking about when we talk about strain hardening. The whole graph now for this material goes like this after I do more investigations of it. So before I could stretch it 6 millimeters before it would break. Now I'm on this new graph. I can only stretch it 5.8 millimeters is what that corresponds to, or no, I think it's 5 millimeters for my new graph. So the material has become more brittle. I can't stretch it as far before it breaks, but it's also become a little bit harder. The proportional limit is at a higher value of stress. In other words, the proportional limit is the stress, and it's higher than it was before. Before, the end of the straight line segment was here, now it's here. So I've actually changed the material, and we refer to that as stress hardening. I made it so now I can't stretch it as far as I could before it breaks. I don't have to stretch it as far in order to get to the ultimate stress, and I've got a longer proportional limit with a higher max value for the proportional limit. They refer to it as stress hardening. So that's the whole idea between stress hardening from a phenomenological point of view. And as far as the molecular point of view, I'm not sure if you were asking about that, but the metal, the atoms are in the form of a crystalline lattice. For some lattice structures, it's a bunch of repeating cubes, a pattern of repeating cubes where the atoms are at the corners of the cube. And when you stretch it, you knock some of those atoms out of place. And the metal, instead of being in a perfect arrangement, it's got some places where the atom is dislocated from where it belongs. And one of the things that makes is because it's not as perfect arrangement, you can't stretch it as far before it breaks, so it makes the material more brittle. And some of these dislocations, they represent something analogous to a knot in a rope. So something that's not right within it, but it's a little bit fatter, and they can't slide across each other. And that's part of the reason that you have made it so that you get a larger proportional limit. What's interesting, if you take a hot metal that's very close to its melting point, the hot bar, and let it cool very, very slowly, you can make it so that the atoms find their ideal place, and you get a metal that's very, very well arranged. So when you heated it up, you've made it close to a liquid, so a lot of the material, the atoms are not strongly bound to their neighbors. It's behaving closer to a liquid, and they move around. And then if you cool it really, really slowly, you get this this ideal, or something very close to the ideal crystalline lattice structure. Whereas, and we said we can mess that up by stretching the material beyond its elastic limit, beyond its proportional limit, beyond its elastic limit, really. The elastic limit is, it won't snap back if you go beyond the elastic limit. So we get into the plastic regime. And you can mess up the crystalline lattice structure in that way. Another way people do it is they heat it up, and then while the metal is in that state where the atoms aren't all that strongly bound, they dunk it in some water. So you cool it really fast. And you find out that's, for instance, people for making knives, for instance, will do that to make the blades of a metal that is a little bit more brittle, less ductile, and tends to, it'll break faster, but it'll hold an edge better. So aside from putting carbon in the steel as well. But This is, so at a molecular level, two ways of making it so you got an imperfect crystalline lattice are through this stress hardening, or by quenching it, that is by cooling it very rapidly after it's been heated up. Alright, that's in response to a question that appeared in one of the reading reports about stress hardening. The big deal is you change the structure of the metal at an atomic level, which makes it so that it behaves differently. It's got a larger proportional region, and then it breaks sooner.